Okay, so as I said, the inner ear contains the following regions. So you have the vestibule, the semicircular canals, and the cochlea. Okay? The cochlea is about 35 millimeters long, and it coils around 2 3/4 turn around the modiolus, or the bony core of the cochlea, of the bony labyrinth. It contains blood vessels and cell bodies and processes of the cochlear branch of the acoustic nerve. The acoustic nerve is what nerve? It is the cranial nerve number 8. Okay? The acoustic part, or the cochlear part. So here is a diagram. This is to show that the bony labyrinth completely envelopes the membranous labyrinth. Okay? Bony labyrinth completely envelopes the membranous labyrinth. So the inner ear, when talking about the inner ear, we always talk about the two fluids of the inner ear. So it's just like the intracellular and the extracellular fluid in physiology. In the inner ear, you also have the perilymph and the endolymph. Perilymph, endolymph. Endolymph inside, perilymph outside, perimeter. Endolymph inside. So the perilymph is present in all regions of the bony labyrinth. It is similar in composition to extracellular fluid in CSF, so you expect it to be rich in what electrolyte? Sodium or potassium? Sodium. Okay, it contains little protein and it drains by the perilymphatic duct, the subarachnoid space. It suspends and supports the bony labyrinth. So it's kind of like the cerebrospinal fluid to the brain, right? It supports and protects the membranous labyrinth. While the endolymph, on the other hand, fills the membranous labyrinth, it is the opposite. So it's similar to intracellular fluid. It is rich in potassium and low in sodium. It drains via the cochlear duct into the venous sinuses of the dura. So remember what other fluid drains into the venous sinuses of the dura? Yes, cerebrospinal fluid. Similar with the endolymph. Okay? And then we also have to talk about the utricle and saccule. So the utricle and saccule, what you have to remember about them is that their functional area are called maculae or macula. They are small areas of neuroepithelial line area. They are lined by neuroepithelium. The macula of the saccule is in perpendicular plane with that of the utricle. So they are arranged at what? 90 degrees. Okay? Each hair cell is an apical hair bundle. You have 1 kinocilium and 40 stereocilia. The tips of these hair cells are embedded in otolithic membrane. Otolithic membrane. What is an otto? It is the ear. Lithic meaning it's a stone. So you have small stones made of calcium carbonate. They are otherwise known as otoconia. So remember, remember that the hair cells are the mechanoreceptors of the inner ear. So for the utricle and saccule, you have macula, which is their functional part. And the macula has several hair cells. And each hair cell is an apical hair bundle embedded in otolithic membrane. That's what you have to remember for the utricle and saccule. Okay? So remember that the utricle and saccule, they actually detect static position and linear acceleration, meaning up and down, forward and backward. So if I'm walking and I suddenly stop, my utricle and saccules are working. If I am standing and I pick something up from the floor, my utricle and saccule are stimulated and hyperpolarized, depolarized, depending on the position. So the utricle is mostly responsible for horizontal forces, walking forward and backward, whereas the saccule is mainly responsible for vertical forces, upward and downward, picking up objects. Okay. So also remember that the maculae have 2 types of hair cells. You have type 1 and type 2. Okay. So this is a illustration of the utricle and saccule. So as you can see here, this is the macula of the saccule. This one is the macula of the utricle. So how would you remember utricle? Horizontal, saccule, vertical. Okay? So how does this work? Linear acceleration, either forward and backward or up and down, produces drag of the autolytic membrane. Remember that the apical ends, the cilia, are embedded in autolytic membrane. So once you move forward, the autolytic membrane, because of inertia, it remains, and once it catches up, so it produces drag. And remember that movement of the stereocilia towards the kinocilium produces depolarization by opening of the calcium channels and influx of opening of the potassium channels and influx of calcium and release of neurotransmitters. Whereas when the cilia is moved away from the kinocilium, okay, this causes hyperpolarization, closure of cationic channels, and reduced neurotransmitter release. Okay, stereocilia towards the kinocilium, depolarization, release of cations. Stereocilia away from the kinocilium, hyperpolarization, closure of the cationic channels, and decreased neurotransmitter release. Okay, so this is what it looks like. This is the kinocilium. Remember, there's only one kinocilium per apical part and around 40 to 50 stereocilia. Okay? So towards the kinocilium, depolarization, release of potassium, entry of calcium, and there is neurotransmitter release at the synaptic junction. Okay? Whereas movement of stereocilia away from the kinocilium, there is closure of the cationic channels, no exchange of cations, and no neurotransmitter release. So sensory impulses from the maculae of the vestibular complex move towards the central nervous system via branches of the 8 cranial nerves, and they're mixed together with the input from the semicircular canals so that the brain can process your position in space and your movement. So clinical application, how does this work? I'm sure you've experienced motion sickness. Motion sickness is caused by repetitive changes in linear acceleration and directional changes, and there is overstimulation of the macula of the utricle. Usually it's the utricle because utricle is responsible for horizontal movement, saccule, vertical movement. So overstimulation of the macula of the utricle produces motion sickness. No? When you're traveling and you suddenly experience nauseated and you want to vomit, that is because of overstimulation of the utricle. And then of course you also have vertigo. So just to be clear, dizziness and vertigo are not the same. Okay? Dizziness, there are different types of dizziness. Vertigo is one description of dizziness. When you say vertigo, it means that there is a spinning sensation felt in the head. And there is a lack of equilibrium or imbalance. So it is caused by imbalance of stimulation of the crista ampullaris to the semicircular canals. So remember, if there is one side problem, it produces vertigo. But two-side problems usually does not produce vertigo. And then we move to the semicircular canals. So we're through talking about the utricle and the saccule, or the vestibular part of the inner ear. So now we're moving to the semicircular canals. The semicircular canals extend from the wall of the utricle. They are orthogonal in arrangement, meaning they are at 90 degrees with each other. And you have to remember that the semicircular canals are paired organs. So the right horizontal canal is partnered but opposite to the left horizontal canal. The right superior canal is opposite and partnered with the left inferior canal, and vice versa. So each one, so remember, for the vestibular organs or the utricle and saccule, you have a macula. But for the semicircular canals, you have a crista or crista ampullaris. And these contain the hair cells. Each crista is perpendicular to the long axis of the duct. They are similar histologically to the macula, but their proteoglycan layer, remember, for the utricle and saccule, what do they have? They have the autolytic membrane. But for the crista ampullaris, they have the cupula. And the cupula usually has no otoliths. So it does not have calcium carbonate stones. The semicircular ducts, they detect rotational velocity. Rotational velocity. Okay? So the utricle and saccule, they detect linear acceleration. But for the semicircular canals, they detect rotational velocity, which means that there is direction and speed. So they can detect the rotation, direction, and speed of head movement. Deflection is caused by endolymph movement. And these semicircular ducts, like I said, are oriented opposite and paired to each other. And inputs from the duct travel together with inputs from the utricle and saccule to the central nervous system. Okay, so this is how the semicircular canals look like. This is the crista ampullaris. As you can see, this is the cupula. So once there is head movement, cupula is deflected, and this causes increased or decreased firing of the semicircular canals. Clinical application, I'm sure you've heard of BPPV, benign paroxysmal positional vertigo. It is benign, meaning it's not really, life-threatening. It is paroxysmal. It occurs in paroxysms, meaning it occurs in attacks. It is positional, so it is dependent on position of the patient. So, brief episodes of vertigo caused by sudden changes in head position, usually standing up or sitting up from lying down. One or more otoliths detach and move into the ampulla. So remember, the semicircular canals do not have otolith. It is the utricle and saccule which has otolith. When otolith is displaced from the otolithic membrane, it can go into the semicircular canal. And because otoliths are heavier than endolymph, okay, remember, in semicircular canal, what deflects the cupula? It's the endolymph. If there is an otolith there, of course, the otolith is heavy. It's a stone. So now the semicircular canal becomes more sensitive because there is a heavier stimulus for it. And sensory impulses may be incorrectly interpreted as head rotations. That's why these patients, when they move their head, they experience like the world around them is turning upside down. The treatment for this is canal repositioning maneuver. So here is an example. This is what we call an Epley maneuver, most popular maneuver, but there are actually multiple maneuvers which you will learn later in the clinics. So lastly, we have the cochlear duct. So we're almost through. We discussed the vestibule, utricle and saccule. We discussed the semicircular canals, and finally we're onto the cochlear duct. So this is the part which is responsible for hearing. When discussing the cochlear duct, what you have to remember is the spiral organ, or organ of Corti. Okay? So the cochlear duct is actually the middle part of three scala, or three ladders, or three layers. So you have the scala media, which is formed by the cochlear duct. This one is endolymph filled. It is continuous with the saccule, and it ends at the cochlear apex. Okay, you have a larger scala vestibuli, which is separated from the scala media by the Reisner's membrane. They lie on each side and enclosed by simple squamous epithelium with tight junctions. Remember what the function of tight junctions are in the brain? Of course, they form part of the blood-brain barrier. Here, they also have a very important role because perilymph cannot mix with endolymph because perilymph is toxic to the outer hair cells. When they mix together, it can cause outer hair cells to malfunction, and you can end up with vertigo, hearing loss, and the likes. So, scala vestibuli is perilymph filled. And lastly, you have the scala tympani. It also contains perilymph, and it is separated from the scala media by a fiberelastic basilar membrane. So, if you know that the scala vestibuli and tympani actually communicate at the apex of the cochlea in an opening called the helicotrema. So if you stretch out the cochlea in its 2 3/4 turn, the scala vestibuli and scala tympani are actually one very long tube, or one very long layer. So here's an illustration of the scala vestibuli, scala media, and scala tympani. So here's the organ of Corti. This is the organ of hearing, or the spiral organ. This is the Reisner's membrane, or the vestibular membrane, which separates the scala media from the vestibuli, and the fibroelastic basilar membrane, which separates the media from the tympani. Okay? So how is endolymph formed? Endolymph is formed in a specialized vascular strip called the stria vascularis. Stria vascularis, meaning it's a straight vascular strip located in the lateral wall of the cochlear duct. If you can see in this microscopic view, this is the stria vascularis. This is the organ of Corti, scala media, scala vestibuli, and scala tympani. And this is the stria vascularis. This is responsible for producing endolymph. Okay, endolymph. So stria vascularis produces endolymph with high concentration of potassium. They are transported across tightly joined cells and bathes the stereocilia of the hair cells that produce optimal condition for depolarization. Okay, the organ of Corti, composed of sensory hair cells. They have outer and inner hair cells, two groups of hair cells. Remember that the inner hair cells are more heavily innervated, but they are actually fewer in number. Okay, the outer hair cells outnumber the inner hair cells about 3:1. You have about 12,000 outer hair cells arranged in 3 rows, and inner hair cell which are arranged in a linear array, so about 3,500 cells. The cell bodies of these bipolar neurons are located in the spiral ganglion. Okay, so in the exam, when we ask where are the cell bodies of the neurons of the vestibulocochlear nerve found, in the spiral ganglion. So let's briefly touch about the outer hair cells. Their stereocilia is embedded in the pectoral membrane, which is composed of collagen, different types of collagen. So that's why in some patients with collagen vascular disease, they also have what? They also have hearing loss. So this is a illustration showing you the outer hair cells. Here are 3 rows of outer hair cells and approximately 1 inner hair cell. So 3:1. And this is the cochlear nerve fibers located in the spiral ganglion. Okay. They detect minute movements of the stereocilia and act as mechanoelectrical transducers. So when sound wave